In this lecture, we'll start talking about supervised ML. Right? Supervised machine learning is a major subpart of machine learning in general, and a lot of applications that we see all around ourselves are actually they actually fall under the paradigm of supervised ML. So just this lecture is just to give you an overview of what supervised ML is, what is the problem that we are trying to solve, and what is the general approach that we take to solving this problem. I'll also try to introduce some very basic terminology in this 5-minute lecture. After this lecture, a lot of the lectures that we'll see, the first part of this course is about exploring various supervised ML models, various approaches that people take. And we'll go into the depth of what approach offers what kind of advantages, disadvantages, and so on. Right. So before I define supervised ML, let's just look at the problem statement that we are trying to address. Right. So picture this: we have a bunch of input-output pairs, right, which we call the labeled data. If you have studied supervised learning, you must have come across this term labeled data. You are training something on labeled data. What does it mean? It means that, say, for input x1, you know that the output is y1. For input x2, say the output is y2. And you have n such samples that are given to you, right? So xn, the output is yn. And this piece of information is given to you, right? Now, you are presuming that there is a function that connects the two, right? There's a function that goes from x to y. And we don't know what this function is. So this function is an unknown. What we know are these n examples of inputs and their corresponding outputs. And what we want to do is use this information to come up with an approximation for this function f, right? So this will be our approximation. Right? So often supervised ML is also thought of as function approximation. Right? Where you have some inputs and their corresponding outputs, and what you have to do is guess the function that lies in between them. Guess the function. That's the name of the game, essentially, right? Now, why do we want to do this? The answer for that is very simple. What you want to achieve is that if you have a new data point, a new input, right? This is some new input. You want to give a rough approximation of what the output would look like. Rough approximation of the output. Right? If you can roughly approximate what the output is going to be for any unseen input, that can come across as being smart, being able to understand what is happening and being able to tell you. So for example, say you can think of a cat and dog classifier, right, which is a very simple application. Right? So you give them pictures as input and you get whether it's a cat or a dog. So you show the model a lot of pictures and it tends to learn the function, how to decide whether something is a cat or a dog. And then when you show it a new picture, ideally it should be able to tell you whether it's a cat or a dog, right? And that is where the core utility of this lies, right? And you can then go on to do much more complex tasks, represent very complex functions, right? So this is the crux of what it is, and I would insist you guys to think of it as function approximation, essentially. Right? Now, how do we do it? Right? So the general approach, right? Let's move to the general approach that we take. So there are a lot of ML models to choose from. Right? A model is basically some kind of skeleton or structure. Right? So for example, you can say that, okay, my function probably looks something like this. Say f of x looks something like ax squared plus bx plus c. Something like this. You say that the function that I'm trying to approximate, I'm assuming that it's quadratic. Right? So this is the model, right? And this a, b, and c become the parameters. So every model has a lot of parameters in it, which you can adjust. And when you change the parameters, the function that it represents changes, right? So you can assign any value to A, B, and C, and you can represent a wide range of quadratic functions with it, right? So this is what it is. So you pick a model, but keep in mind that like this model cannot represent something significantly more complex than a quadratic curve, right? So that's the idea, to pick a model that is capable of representing the function you're trying to approximate. That is sometimes something that you have to take care of. And then every model has parameters. Now you choose a model, say that function is h naught, at time step 0, right? This is the function. You pick some initial values for A, B, and C. It represents a function. That function is h naught. H, by the way, stands for hypothesis, because all of this is a hypothesis. You are suggesting that, oh, this could be the function, or this could be the function, right? And now h naught is very unlikely to be the right answer. So what you do is you go step by step. You go to h1, then you go to h2, then you go to h3, and you take k steps, you reach hk, which starts to look very similar to f, right? This process is called training the model, right? So basically what you're doing is you are editing the parameters of the model so that it fits the data better, right? And by fits the data, I mean that for the given input, your output, your functional output should be as close to the actual output as possible, right? You have a few input-output pairs to do that check, whether or not it fits or not. Now, training the model requires you to be able to evaluate any particular hypothesis, right? So for example, if I want to evaluate H3, how much better is it than H2, or is it worse than H2, right? For that evaluation, you need something called the error. You define an error function, right? This error function gives you a rough estimate of how different you are from the ideal function, supposed ideal function. Right? So you define this error, and at every step you calculate the error, and you move in a direction where the error is reducing, right? And you go from hk to hk plus 1. That's how you move. So this is the general approach. So in this series, we'll talk a lot about various ML models. What are the different kinds of models, when are they used, so on. What are the parameters, how do you initialize these parameters, and why do you initialize them a certain way, right? How do you train the model? Now, it's important to find a general solution to this problem, right? The general solution to what the function would be. There are many ways to fit through the data, right? But you want to find a general solution to the problem. And that is what training is all about. So training the model is another very important topic, and it has a lot of small caveats in it that we'll cover as we cover the different kinds of models. Now, before we close this small introductory lecture, I would like to take a step back and talk about two methods, right? One is deduction and one is induction, right? In deduction, what we do is that we have a general universal law. Say my universal law is that A implies B, right? This is my universal law. Now, I also know in a given situation that A is true. So I can apply that universal law to a specific case where A is true to deduce that B must also be true. Correct? So you are taking a general rule and applying it to a specific case to deduce something about that specific case. Right? The other side of the spectrum. So deduction is how most of engineering applies science. Right? You have a rule, you apply it, and you get the answer for that specific case. Say you apply Newton's law, or whatever. Induction is practically the opposite, and this is what we are doing with machine learning. Here what we are doing is we have a few instances, we have a few examples of how the world works, right? You have some x and you know what the y's are for those corresponding x's. And what you want is to derive a universal law out of it. You want to understand what the underlying function, general function must be. right? So it's practically the opposite. And so here you have examples, and you want to go to a general rule or the general function that connects the two, right? This process is called induction, right? Keep in mind that the goal of this process of training and understanding the function is not to actually understand the function mostly, but to be able to figure out outputs for inputs that we have not seen before, right? So if there's a new input, you need to be able to roughly estimate the output. Now a small statement there. Since these functions, this particular function that we are trying to approximate can be as arbitrary as we can imagine, right? There's nobody who's controlling this function, right? This function could be very arbitrary. We know how the function behaves at x equal to 2, and we know the output at x equal to 3. But at x equal to 2.5, it could be anything, right? We don't know. That's the thing. So if the function was totally free, and we presume that, oh, there's no constraint on what the function would be like, it could be as arbitrary as possible. In that case, this whole exercise becomes meaningless, because we can't deduce anything. If we have not seen that input, we can't say anything about what the output would be. So we make certain assumptions, right? We make a lot of assumptions about the function. Assumptions about the function, right? These assumptions allow us to make a prediction in the first place, right? So for example, if at x equal to 2, the function is suggesting 2, and at x equal to 3, the output is say 3, right? So that's a very simple function. It suggests that, when at x equal to 2.5, the value would be somewhere between 2 and 3. It would be a smooth function. You would not expect the value to be 10,000, for example. But it could be, right? You don't know that for sure. So any assumption that you make about the function is first of all important, because without it, the whole exercise is meaningless. And the second part is that these assumptions about the function is called inductive bias, right? Because we are doing an inductive exercise, we are taking examples and then using that to come up with a general rule. That general rule may or may not be true. We can't ever know whether it's true or not, but we get to that rule only by assuming certain things about the function, right? And bias is obviously because it's something that we are presuming. It's not necessarily true. So again, when we discuss various ML models, we'll talk about the inductive bias that goes into those models. But this is just the general idea of how ML is different from your regular kind of engineering.